So good morning, everybody, and welcome to the last lecture. So this is about Lambda-Adic Galois representations. So remember, we were doing the main theorem of Hira theory. We had defined Lambda-Adic forms, and we had said that there are finitely many Lambda-Adic forms, primitive ones. At least if you impose the ordinary condition. Sorry, I'm just getting the paper right. This is not the center. Yeah. Then we had a theorem. The second part of the theorem said that that every classical form lives in a Lambda-Adic family. Every p-ordinary classical form lives in a p-ordinary Lambda-Adic family. And then part 3 said that every such family is unique. And part 4, which is what I want to do today, says that if there's a primitive Lambda-Adic form, a p-ordinary one, then you have a Galois representation attached to it. So I will describe the Galois representation today in a fair amount of detail. And I will also maybe give a sketch of the proof of the existence of the Galois representation. Okay, so not just give the properties, but some proof of it. Can you hear me a little better now?
Yeah, it's quite clear now, yeah.
Okay, great. So let me maybe recall some things about the Galois representations classically, and then because I did this in the first lecture and it's been almost a week now, so then we'll come back to the Lambda-Adic situation. So recall that if f is just a classical modular form, some shadows coming. Let me see if I can put on one more light. Yeah, should help a little bit. N is greater than 1 and chi is a character. Primitive cusp form. Primitive means, as usual, normalized with the Q coefficient to be 1 and an eigenform and a new form, n new form. Okay, so suppose you have such a form and P is a prime, but we will assume P is bigger than 2. But for this theorem, you don't need to assume P is bigger than 2. Greater than 2 eventually for Lambda-Adic forms, because otherwise I have too much notation. I have to replace P by Q equals 4. So recall P is a prime. And there's this theorem that I stated at the beginning due to Deline and, well, in weight 2, it was already due to Eichler-Shimura. Given such an F, there exists a rho F. You have a group of Q to GL2 of p-adic field. Remember, Kf was equal to QAN. You attach the Fourier coefficients of this form to Q. You get a number field. Find an extension of Q, and P was a prime in here, and then we had fixed a prime P in the ring of integers of Kf lying above P, which is a prime of Z. So this is the completion of Kf at P. So there are these p-adic Galois representations, one for every prime, including P equals 2 actually, such that the traces of and determinants of certain special elements, in other words, the characteristic polynomials of certain special elements, namely the Frobenius elements at the primes L, where L has nothing to do with anything in sight, namely the level of the form and the prime P. Well, the trace of this matrix, you take Frobenius and you push it over here, you get a matrix, you take its trace, you get AL, AL Fourier coefficient, and the determinant is given by a simple formula involving the Neven typus and the weight. Chi of L times L to the k minus 1 for all primes L not dividing NP. Okay, so this is a very fundamental fact in the theory of Galois representations, modular Galois representations. And the second fact is, which was due to Mazur-Wiles in the elliptic modular case, which we're working in, but then Wiles in the Hilbert modular setting. And since there was another course by Professor Chandrakant on Hilbert modular forms, let me also mention the Hilbert modular version here, though I'm not stating it here, but it's the reference. So if F is P ordinary, that means, remember, the p-adic valuation of AP is 0. Then the local behavior of this Galois representation at a decomposition subgroup at P, namely, if you restrict the Galois representation to the Galois group of QP, then it has a very simple shape. It's reducible.
Can you flip the page a bit? I mean, lift the page a bit up.
Sorry. Is reducible. Okay, so this Galois representation, the original one is actually irreducible, so continuous irreducible. But of course, when you restrict to a subgroup, there's no reason why it should be irreducible. For example, if you restrict to the trivial subgroup, then of course it becomes reducible. But if you restrict to this intermediate subgroup, the decomposition group, it's not clear if it's reducible or irreducible, and it turns out to be reducible. Okay, so today what we want to do is we want to prove lambda-adic versions of these. So Hida, and then Wiles, so Hida proved a lambda-adic version. So Hida and Wiles, because the second theorem was actually really Wiles, proved the lambda-adic version of these theorems. Wiles also gave a new proof of the first theorem, the lambda-adic version. Okay, so let me state now those theorems. So I mentioned this very briefly at the end of last lecture. So let me call it theorem lambda 1 and theorem lambda 2 for lambda-adic versions. So let F be an ordinary lambda-adic form, primitive. Right, so there's no weight. There's a level n, which is co-prime to p. I won't write all the notation down from the last 3 lectures, the same notation. N is co-prime to p. I can write it here. Lambda is VP power series x. I is a Dirichlet character. Okay, I'll recall some things. Let me write it in q bar star, but it's actually in c star. But remember, it actually takes values in q bar star, roots of unity. I'm thinking of q bar star fixed both in C in the complex numbers and in qp bar star. So every Dirichlet character is both the p-adic character and the complex character. Doesn't really matter because it takes values in algebraic numbers. So use fix such a lambda-adic form, primitive.
यो त गाल्वा ग्रुपको एक्सन देखाएको होला.
Sorry, was there a question?
Theorem 2.
Then there exists a Galois representation, which is again continuous, but continuous I will not define in this lecture because you have to put a topology on the right-hand side. And I don't want to get into that now, but irreducible, of course, one can understand. You can't put a 0 in the lower left corner for this representation. Into GL2K, and just to follow the notation up here, where I had taken KF, chaotic field, let me also, I usually is calling this K, but let me call it KF because it really depends on the form F. Remember, just very quickly, K, which is KF, is a finite extension of the quotient field of lambda. And I was the integral closure of lambda in the quotient field. Okay, so I was the integral closure of lambda in a finite extension of the quotient field of lambda, and we take it so large that it contains all the Fourier coefficients of the lambda-adic form. Okay, so there's such a Galois representation such that two very similar properties hold. The trace of rho of Frobenius of L. So, this is now a power series. Frobenius of L, just to, there's a lot of notation. So Frobenius of L is a Galois element. Rho F of Frobenius of L is pushed forward here. So it's a matrix. But it's a matrix with entries in a power series field. Kf is a field, it's a power series field. And then you take the trace of that, and so you get a power series, and the power series you get is now it's the L Fourier coefficient of the lambda-adic form F, very similar to the Deligne version up here, where you got the the Lth Fourier coefficient of the classical cusp form F. Now we get the lambda-adic cusp form F. And the determinant is given by also a nice formula. So it's psi of L. Remember, psi was the Dirichlet character of the lambda-adic form. Kappa of L, I'll define kappa in a second, and nu of L, maybe nu p of L, because I had a nu before. So this is the p-adic cyclotomic character. And I think I have to put an inverse here. I'll write it out in a second. In my notes, I don't have it, but I think I have to put an inverse here. We'll just check this in a second. For all primes, L not dividing NP, exactly the same. Okay, where
Eknath, is that chi L or after psi L, is it chi L? I mean, in the last line.
Psi. No, there's no chi so far in this picture.
So it is.
There's only a lambda-adic form with the character psi.
And what is that KL, I think, right?
And kappa L and nu sub p of L. I'm going to define them in a second. Let me put page numbers in so that when you're splicing the videos together, there's no confusion. 24. I'll define kappa and nu in a second. Good question. Let me maybe even move this up here. Oops. No, I can't do that. That's not a good thing to do. Then I put my paper up there also. So just this sheet. Let's see if this works. Yeah, so maybe this works. Page 25. Okay, where kappa, as we were just asking about, is what's called the lambda-adic cyclotomic character. So this is the classical cyclotomic character. We had the mod P cyclotomic character, which was just a Dirichlet character of conductor P. Then we have this this classical cyclotomic. This is a characteristic zero cyclotomic character. So it actually has conductor P to the infinity if you want. But as a Galois character, it's a character of the Galois group of Q onto ZP star with the usual definition. Maybe I'll say more if somebody wants to know about it. But these are various classical things, the mod P cyclotomic character and the characteristic zero cyclotomic character. But kappa is the lambda-adic cyclotomic character. It's one level up from those two, slightly more complicated, but it's a very canonical character. And it's the following character. And you should understand this character very well if you want to do lambda-adic forms. It's at the heart of everything in some sense. So what you do is you have the Galois group of Q. You have the Galois group of the cyclotomic field, the p-power roots of unity cyclotomic field as a quotient. Right, which everybody knows is an inverse limit. I did this last time in one of the lectures. It's an inverse limit. Okay, maybe I'll do it here just to go slowly. Z mod P to the n star, right? Which is the same as ZP star. Right? It's the periodic units. Z mod P to the n star is just ZP star. And ZP star decomposes into a Z mod P star and a 1 plus P ZP. So we further project to the 1 plus P ZP part, second factor of ZP star. And then finally, this is, so far what I've done here is just Galois theory. But now we define the character. Here's the character finally, lambda star, and we send 1 plus p to 1 plus x. Remember, 1 plus p was a generator, topological generator. We had said that every p-adic integer congruent to 1 mod p could be written as a power of 1 plus p. We had even had some notation for it. It was the sth power, where there was a notation for it. So some s belongs to Cp. But anyway, once you, it's topologically generated by 1 plus p. So if you say where 1 plus p goes, then 1 plus p to the s will go plus to 1 plus x to the s, and we had defined what 1 plus x to the s was also in terms of the binomial series expansion. Okay, so this is a very canonical character. It's a Galois character which follows these very natural arrows, and the last one is really the definition. 1 plus p goes to 1 plus x. Okay, so we need that, and nu p is you do the same thing. You subject to the Galois group of q mu p infinity over q. I'll skip a step here. It's equal to that projective limit, but it's just zp star. And this is actually an isomorphism. You just stop at this point, zp star. You don't do any further. Okay, just the first 1, 2 terms of this thing above. So this is the character, the L-adic cyclotomic character. This has a very explicit formula. If you don't like this, right, maybe I'll write it here. Zeta of sigma, where sigma is the p power root of unity, is just zeta of nu p of sigma. All zeta belonging to p infinity. If you have any p power root of unity, the way a Galois element acts is by the power, some power, and that power is by definition the value of nu p sigma. So this is the usual L-adic cyclotomic character. This one is
So here, what is the topology on the right hand side?
here.
I mean, like in that map, Galois representation rho f.
Yeah, that is a little tricky actually. It's a little tricky. So I'm not going to get into that. I can tell you in words without writing lots of things. What one does is one fixes a lattice here in L, a two-dimensional a lattice L, which is fixed by the Galois group. And that has some kind of topology. The projective limit topology, you take lambda mod maximal powers of the maximal ideal of I. And that gives a topology on that, and then you take that. So it's a little tricky discussing the topology. It will take me another 15-20 minutes to do that. So if you would like to understand this, I once did it quite carefully. It is explained in our lecture notes at the previous IIT Guwahati volume.
Okay.
So that conference from 2008, I think, 12 years ago. There's a whole discussion with several remarks about the topology. But right now, you just think of worry about things algebraically. That's why I put the continuous here in quotes. But there is some sort of topology, and one can define it. So this is the usual p-adic cyclotomic character, and this is the lambda-adic cyclotomic character. Let me just give this a name, kappa. Okay, so I hope defining these characters didn't cause some confusion. Maybe I should have done that before stating the theorem, but this theorem is very clear. There's a Galois representation whose trace is the L Fourier coefficient on Frobenius elements at L, and the determinant is given by this simple formula. Notice that psi of L is a classical p-adic number, and nu p of L inverse is a classical p-adic number, but kappa of L is a power series. So this is really a power series. Okay, very good. And moreover, there's a second theorem So this is theorem lambda 1. Now maybe I'll remove this page. Is it okay to remove this page? So I can go up. There's a second theorem, which is actually due to Wiles. I could motivate these theorems a lot more, but I'm not doing this. For example, if you try and prove such a theorem, this theorem, theorem 2, if you try and, it's a very nice exercise to try and prove this theorem for modular forms corresponding to elliptic curves. Why locally the Galois representation is reducible if you have an ordinary prime. And think about that. And notice here I didn't say P dividing the level or P not dividing the level. That's actually even true if P divides the level. So the second theorem, analog of that, of Wiles, is that the Lambda-adic Galois representation is also reducible. So delta F and epsilon F are two characters, just like they were last time in the classical situation with little f. Now we have capital F. It is again reducible. Okay, so they're exactly the same theorems, more or less, except that you have to get the determinant formula for the determinant right. Otherwise, it's almost exactly the same theorem. So why that strange formula for the determinant? So let's do a little check. So note, I'm claiming that if you specialize the Lambda-adic Galois representation at some arithmetic point, which lies above one of these classical points, arithmetic points, k greater than 2, zeta belonging to mu p r minus 1, r greater than or equal to 1. Suppose you specialize the power series at under this homomorphism nu, right? Nu was a homomorphism from I to qp bar. So it turns out, for example, the trace and the determinant at least take values in I, right? Because the L Fourier coefficient was here, and the determinant also was integral, took values in I, even in essentially in lambda, because kappa took values in lambda. And the other two characters are also integral things, right? So what happens if you specialize this Galois representation at such a point? What happens? I'm claiming you actually get the modular form that I called maybe F nu, more precisely, but a little bit more ambiguously, Fk zeta. Okay, so this is a non-trivial statement, not a tautology. I'm saying that if you take the Lambda-adic Galois representation and specialize at nu, it's the same thing as first specializing the Lambda-adic form at nu, that's F nu, and then taking its Galois representation. In other words, the Lambda-adic Galois representation interpolates the classical Galois representations attached to the forms in the family. Now, why is this? So let us do a small computation to check that this is true. Proof. It suffices to check this. This is isomorphism, of course. Suffices to check this on a dense set of primes on a dense set of Galois elements. So if two representations agree on a dense set by continuity, they agree on the full set. So on a dense set, in fact, we'll do it on of Galois elements, which we take to be the Frobenius elements. Right, this is where we have information. Frobenius L for all primes, L not dividing NP. Okay, so let's do a small computation here. So if you do nu of the trace of rho F of Frobenius of L, right? Well, that is nu of AL of F. And what is nu of AL of F? This is just now a classical Fourier coefficient of the lambda-adic form, right? So when you specialize it at nu, what do you get? Can someone answer? So I know that everyone's awake. If you specialize this lambda-adic Fourier coefficient at nu,
It's L of zeta e to the power k minus 1.
exactly, it's just the L Fourier coefficient of the class form, because you know these Fourier coefficients are interpolating the Fourier coefficients of the classical class forms, right? So by the definition of lambda-adic form, this is just the Lth Fourier coefficient of F nu, but maybe I'll call it Fk zeta, just to be a little imprecise. More precisely, it's F nu. Remember, because there are finally many nu's extending a given k zeta, but I'll just call it Fk zeta. Okay, so that's one observation. So the traces agree, because this was also the trace by Deligne's theorem. This was the trace at Frobenius of L. Or maybe I'll write one more step, which is the trace of rho F k zeta of Frobenius of L. Right? So the lambda-adic trace under specialization agrees with the classical trace. Okay, so that's one remark. And then let's do the same thing for the determinant. If you specialize the lambda-adic determinant, well, now you'll see why I took that weird combination of the cyclotomic character and the lambda-adic cyclotomic character and the p-adic cyclotomic character. So this is psi of L, right? Times one plus x, and I'll just explain this in a second, S of diamond of L times L inverse. Okay, so this is, I'm claiming this is true since, well, what is kappa of Frobenius of L? Well, kappa of Frobenius of L is just kappa of, remember kappa was defined here at the top of the page. This Frobenius of L all the way through here, it actually maps to L, the element L here, but when you push it over here, it maps to diamond of L. Okay, so this is just kappa of diamond of L. Okay, and this is, let's rewrite it as kappa. Let's write diamond of L as a power of 1 plus p.
Sir, slide it a little bit.
Oh, sorry. Yeah. So it's kappa of diamond of L, because that was following the kappa map through to all but the last step. Now I write, because you know I only define kappa on 1 plus p, so we need to write diamond L as a power of. So we write it as the sth power. By definition is the s of Lth power of 1 plus p, which of course is just because 1 plus p goes to 1 plus x, so it's 1 plus x to the s of diamond of L. Okay, so that's why you have kappa of Frobenius L is that. And similarly, well, we already did that in some sense. Nu p of Frobenius of L is just L in ZP star. Okay, this is in lambda star. And if you don't know this computation, you should do this. The Frobenius acts on the p power roots of unity by Frobenius at L just acts by L. Okay, so very good. So let us move on, which is equal to, now this is a separate computation, this is just a remark. Which is equal to psi of L times, well, let us do a specialization. We're specializing under nu, right? Oh, by the way, there's nu everywhere. I didn't write this. This was at the determinant. This is nu. Apply to this whole thing. So now when I apply nu, then x goes to zeta 1 plus p to the k minus 1. Okay, so you get psi, nu of psi of L doesn't do anything to nu. So lambda, it's ZP linear or O linear, there was a finite extension. So these two scalars just pull out, L inverse and psi L, but x is here. So something happens to x. And what happens to x? You get, well, we've done this many times now. 1 plus x goes to zeta 1 plus p to the k. So you get zeta S of diamond L. Then you get 1 plus p to the S of L k, and you get L inverse. Okay, I just substituted for x. I'm doing this 3 times this computation so that it becomes routine, but I could have skipped this because we've already done it twice before. Okay, so let's keep going. We're not done. Which is equal to, this page, I think 26 maybe. What page is this? 26, yes. Well, psi of L, right? And this is chi zeta of L. This maybe I won't do again, right? Same proof. It's chi zeta of L or chi zeta of diamond L, it doesn't matter because the way L maps to diamond L, chi zeta is only defined on the diamond part, on the second factor. And it's the same thing. It'll be only know where 1 plus p goes. 1 plus p goes to zeta. So you have to write, yeah. So this is easy computation, which I've done many times. I'll skip that. And this thing is by definition diamond L, right? 1 plus p to the S of diamond L is diamond L to the k, L inverse, which is equal to psi of L. And we write L as omega L times diamond L, this decomposition. And I use that here to simplify this. So this is omega to the minus k of L, chi zeta of L, and L to the k. Okay, I substitute for diamond L to the k. I wrote it as L to the k, omega to the minus k of L. Got that over here. And there's a minus 1. So now you can see why I really needed the minus 1 there. Which is chi of L, as Anupam was asking. Isn't there a chi somewhere? Well, now is where the chi comes, because chi was by definition the Nevin typus of the specialized form. Psi omega minus k chi zeta. Okay, which is the determinant of rho f Frobenius rho f k zeta of Frobenius L. Okay, so looking from beginning to end, we see that the trace specializes to the trace, so the classical form, and the determinant of the lambda-adic form, lambda-adic Galois representation, specializes to the determinant of the classical Galois representation. Okay, so this shows you that the original identity I wrote, that these two representations are the same, well, they have the same trace and determinant. We just computed that. So they have the same characteristic polynomials on a dense set of elements, and therefore those two Galois representations are the same, or isomorphic. This is what I meant by suffices to check this. Okay, so I hope now you understand why the determinant formula was what it was. It was manufactured to exactly give you this answer at the end. We secretly slipped in a psi there so that you got a psi at the end. We secretly slipped in a nu p inverse there, so you got this k minus 1 at the end, and then the kappa was there, which pretty much gave this term, the middle term, omega minus k and chi zeta L, things like that, and an L to the k. Okay, so thus the moral of this whole discussion so far is that the rho f p-adically interpolate the rho fk zeta. Okay, very good. So let me remove this sheet of paper so I can go up. All right, so this is some information about the Lambda-adic Galois representation, both globally and locally. So now let us try and prove the existence of the Lambda-adic Galois representation with those two properties. So for this, I need some background on pseudo representations, which sound very fancy, but it's actually something very easy. So before I give formal definitions, I'll just draw a schematic picture of the idea. You know, we have these rho f k zetas, right? These classical Galois representations, and we want to construct rho f, which periodically interpolates all of them. This is going to take values in power series fields. This is going to take values in usual periodic fields. So how do we glue together all these representations, these classical Galois representations? Well, this is an idea of Wiles. This is not the way that he did it originally in 1986 paper of his, in his 1986 inventionist paper, but a very simple idea of Wiles to construct this Galois representation using these pseudo representations. And what his idea was is that you, from this Galois representation, you construct something a bit easier, which is easier to patch together, and that is called the pseudo representation. These are Galois reps on this side. These are pseudo Galois representations or pseudo representations on this side. Okay, so you have these pseudo representations, which are basically the trace and determinant of this. I'll define it formally in a second, of this classical Galois representation. And one more piece of information. These, it turns out, are not so hard to glue together. So you get a capital pi sub f, which patches together all these pi k zeta, it periodically interpolates them. And then going in the other direction is not obvious each time, if you're given a pseudo representation because you've lost information. But it turns out that if you are in the situation we are in, you can actually recover the classical Galois representation from the pseudo representation. Okay, so you have these classical Galois representations, and therefore you have pseudo representation. That's very easy. You patch them together, which I'll explain how to patch together pseudo representations. Once you patch together the pseudo representations, you have to ask yourself whether it really comes from a genuine Galois representation as the trace and determinant of a genuine Galois representation, and it indeed does. And then you can check that this interpolates. So this is the indirect way in which you do this vertical arrow here, going up. You go around this direction of the square. So the whole idea can be reduced to patching pseudo representations. Okay, and that's why we introduce pseudo representations. So let us quickly talk about some that's very elementary. So let us talk about the definition of pseudo representations and some theorem which allows us to patch together pseudo representations and allows us to decide when a pseudo representation comes from a Galois representation, etc. So I'll work in some generality. So the notation now is completely independent of the rest of the lectures. So start with the topological ring, commutative topological ring B. Let's assume with unity. And let's assume that half belongs to B. So 2 is invertible in B. For example, if it's a p-adic ring of some kind, then that's always true if P is odd. I'm going to work with Galois groups, but since I'm working in general terms here, let G be a profinite group with E an identity element and C a special element of order 2. These will show up in the definitions. Okay, so for us, B will be something like lambda or I, or maybe their quotient fields. And G for us will be something like the Galois group. It will be the Galois group, and E will be of the identity of the Galois group, and C will be complex conjugation. Okay, but for now, let us just work in the general terms. The definition: a pseudo representation pi from G to B. This is the notation. You write it this way, but this doesn't mean anything. It's not a homomorphism or anything. It's just a notation. We write it like this. Is formally a triple of functions, capital A, capital D, capital X, of continuous maps. Notice G has a topology, it's profinite, so, and B is a topological ring, so they both have topology. Continuous maps, A from G to B, D from G to B, and X from G cross G to B. Okay, so this is already looking a bit scary, but it's not. So what these functions are going to be are, if you have a genuine Galois representation, remember I said if you're given a genuine Galois representation, it's very easy to attach a pseudo representation. So this capital A function is just going to be the top left corner of the matrix. And this capital D will be the bottom right corner of the matrix. And this function on G cross G will be the product of the anti-diagonal elements. Okay, so B times C, little b times little c. In the matrix ABCD, little b times little c, not capital B. That will be what this will be. Okay, I'll write that down in a second. But for now, they're just these abstract three functions satisfying the following axioms. Now, the axioms themselves are not important, but since unfortunately this is recorded, I have to write them down. And this is why I don't like talks to be recorded, because you can't skip steps. Okay, so this is a very natural axiom. If you take the eighth entry of the product of two matrices, you basically get the product of the individual A entries up to some other factor, which depends on B and C of the matrix, right? So this is just mimicking that, but I'm just writing them abstractly right now. D of sigma tau is D of sigma D of tau plus X of tau sigma this time. This is for all sigma tau in G, the Galois group, just abstract group G for now. 3 X of sigma tau. You can go to sleep for a few minutes and wake up and when I tell you to. A of sigma X of tau gamma plus D of tau, and let's hope I don't make mistakes in copying these things. 4 X of sigma tau of gamma is equal to A of gamma. They're all very natural things which clearly hold if you take A, D, and X to be the obvious functions attached to a standard Galois representation. I hope I got this right. Huh? These may have made some small mistakes because I'm doing it fast in copying all the letters. A of D, well, the A entry of the identity matrix and the A entry of the complex conjugation matrix are always 1, but the D entry of the complex conjugation matrix, because it's 1, 0, 0, minus 1, right? It's element of order 2, is minus 1. Some other obvious things, if you multiply any matrix by the identity matrix, then not much happens. This doesn't look right to me, actually. x of sigma times E. I didn't check each one of these individually for standard Galois representations. I should have probably. For all sigma, tau, gamma, eta belonging to G. So sorry about that, but there are these 7 axioms. Okay, can someone mentally check number 6 while I'm talking? So x of G1, G2 is just B of G1 times C of G2. So does this really hold? Oh yeah, these hold. Yes, yes, they trivially hold, right? Because the C entry for the identity element is 0. Okay, and the C element, the lower left element, there are 2 C's here. The lower left element of complex conjugation, because it's 1, 0, 0, minus 1, is also 0. So when you multiply it by any element, you'll get 0. So all these hold. Okay, so that is the formal definition of a pseudo representation. So it looks like we've made things more complicated, but actually, in some sense, we're going to have made things more simple. So let's see why. Can I flip the page? Any questions on the axioms? People are still alive?
Yeah. So any representation will of course satisfy all these, right?
Yeah, they're just, these axioms are more or less meant to mimic the obvious properties satisfied by the entries, the matrix entries of a standard Galois representation. You just extract enough information so that you can patch things. So the main example, 26, as Anupam was just saying, I hope this is page 27. Yes, page 27. Sorry. Main example of this is, suppose you're given a Galois representation from a group, profinite group G to GL2. Let's take a 2-dimensional one. There's also a theory of pseudo representations for n-dimensional Galois representations. Is a continuous odd Galois representation. Well, there's no Galois group here, it's just G, just a representation. So odd means that row of the special element is 1 minus 1. Okay, it's an element of order 2, so it has to go to an element of order 2, and we take it to that special element. And then setting A of sigma. So let's assume that sigma goes to A of sigma, B of sigma, C of sigma, D of sigma. Setting A of sigma to be the top left corner, D of sigma to be the bottom right corner, and X of sigma tau to be the product of the top right corner. Sorry, this was top left. Top right corner times the bottom left corner for sigma and tau. We see, one can see with a little bit of computation, that pi equals a dx is a pseudo representation. We say that this pseudo representation comes from rho, the usual classical representation.
Sir, slide it little bit up.
Yeah, sorry. Let me remove this page. So what I said was that if you let capital A be the top left corner, capital D be the bottom right corner, and capital X be this formula, B of sigma, C of tau, then this triple ADX of functions is indeed a pseudo representation. And we say that pi comes from rho. Okay? So this is the main example of a pseudo representation. It's not at all clear that every pseudo representation comes from a usual representation, but we will prove a small lemma in a second, which shows that that is also true. Okay, so I'll make a definition first. So, pseudo representations also have traces and determinants. So let the capital trace, I'll use capital T for, I'm writing capital letters for pseudo representations, so that it's a bit less confusing. A of sigma plus D of sigma, and determinant of the pseudo representation B, you can guess what it is, A of sigma, D of sigma, right? Diagonal entries product minus the anti-diagonal entries for all sigma in G. Okay, so this is the trace and the determinant, I'm not writing the words here, of the pseudo representation. It's a definition. And it's mimicking the definition of the usual trace and determinant of a matrix. Okay, so with this, I can finally, I think, state some nice theorems and corollaries of them. So here is the first theorem about pseudo representation. That if you have a pseudo representation to a topological ring, abstract one, so if two conditions hold, suppose the x function is identically 0. Or if it's not 0, assume that it's a unit on some Galois element. So there exists an H1 and H2 in G such that it's a unit. Suppose one of these conditions hold. Okay. Then the claim is that the pseudo representation comes from a genuine representation. Okay, so let us see the proof of this. It's almost trivial, the proof. What's the proof? Well, in the case that x is identically 0, the 0 function, it's very obvious, clear what to set rho to be. You just set rho of G, okay, I'm using G notation and sigma tau notation now. Rho of G is equal to, you just take the diagonal representation given by A and D. Okay, so if the B, C functions, then you can check that this will actually recover. All those axioms will be satisfied, and yeah, so this will be a genuine representation using those axioms. Sorry, I said it the wrong way. If you know the axioms of the genuine representation, this will, for example, where are the axioms? Suppose x is 0, then you can see that the top left corner is purely multiplicative, right? A of G1, G2 is A of G1 times A of G2. So you get a genuine homomorphism if x is 0. And similarly for the D entry. So on and so forth, right? So if x is 0, there's not, these axioms immediately show that this is a representation with the same, and then pi comes from rho. You can go backwards and get pi. But the important thing is you can go forwards. From pi, you can, well, I don't know what backwards and forwards is, but given pi, you can get rho, and then clearly pi comes from rho. Go in the other direction also. Okay, and the second formula, which suppose that x of H1, H2 is a unit. In this case, you'll be a bit more intelligent, but you not so much more. You still take some obvious matrices. A of G, you take x of G H2 divided by this unit. Remember, this is a unit in the ring, so you can divide by it. H1, H2. X of H1G, D of G, for all G belonging to G. Okay, so given these special elements H1 and H2, such that the X of them is a unit, you take this particular formula for rho of G, and now I will leave it for you to check that, just as I began to do in this very simple case, that that this is a genuine representation. And moreover, that it gives pi. For example, the trace hasn't changed. Look at the trace. AG times G of G, D of G, AG plus D of G. And the determinant also hasn't changed much, as you can try and check. I did that while preparing these notes. That's not obvious. A of G times D of G times this product, right? If you try and do this, well, it doesn't look like X of GG. But if you use axiom 7 here, then it turns out that X of GH2 times X of H1G divided by X of H1H2 is exactly X of GG. Okay, so I said it, and then you can play the video in slow motion and check that. So on and so forth. All right, so the proof is just by explicit construction of the representation rho. And here's the corollary. The corollary of this is if B is a field, topological field, it's over a topological ring, so topological field, then pi always comes from rho. Right? Because if the x function is non-zero even at one point, it's automatically a unit because things in fields are units. So for pseudo representations taking values in fields, you always get that it comes from some rho. Okay, so this is what we're going to use to go in the other direction, because our pseudo representations are, we're just going to artificially, even if they take values in rings like lambda and I, we're going to artificially think of them and taking values in their quotient fields. Okay, and then you can get the Galois representation with values in the quotient field. Notice that the Galois representation I wrote initially was taking values in the quotient field, KF. Okay, great. So let us now move on to constructing the Galois representation. We now know how to recover a rho from a pi. So that's the top arrow of that square that I wrote down. And if I can try and find again. I don't know where it's gone. Here. We just described this arrow. Given a pi, how do you get a rho out of it? Now this arrow is totally trivial. That's the main example. Given a rho, you get a pi. And we've already described this. Now let's try and glue the pseudo representations together. Okay, so for this I need a patching lemma. And let us do this now for our special situation. Okay, instead of working in generality, let G now be the Galois group of Q, and let I be a finite extension of lambda inside the quotient field of lambda, integral closure, sorry. In a finite extension of the quotient field of lambda, let I be a finite extension of lambda, the integral closure of lambda and K, and this was KF actually, I'm just writing as K. And let also A and B be two ideals in I. Okay, so with this notation, I can state the following patching lemma. Patching two pseudo representations. All these things are due to ones. There are many more results on pseudo representations now. For example, you can generalize to GLN, and there are alternative definitions, and it's a whole mini cottage industry. And it's an important tool in the theory of Galois representations. So I thought I would give this proof, these proofs of how you patch together these pseudo representations, and therefore you patch together the Galois representations. So suppose pi of A and pi of B are two pseudo representations. Sorry, I Shouldn't have written them together, but since I have, you have two set representations. Pi of A goes from this one is pi of A, this one is pi of B. Are two pseudo representations. Of G with values in I mod A and I mod B respectively, such that there exist functions T and D on a dense subset of G with the property that the trace of pi of A, so T is I valued, okay? It's like characteristic 0, whereas the A is, I mean, not characteristic 0 is not the good word, but actually I mod A will also be characteristic 0 because A's will be height 1 primes, so still be characteristic 0. It's only when you go modulo height 2 prime, then you go mod the maximal ideal, you get something mod B, so it becomes characteristic B. But anyway, so the trace of pi of A, which is an element of I mod A, right? Trace of a pseudo representation makes sense. It's the A plus D entries, the A plus D function. So that is just T mod A. And the trace of pi of B is D mod B. Okay, suppose this is true. So T is I valued, but T mod A is I mod A valued. So these make sense. And similarly for the determinant, shall I write them? Okay, I'll write them for completeness. Determinant of pi of A is D mod A, and determinant of pi of B, the determinant of the pseudo representation is, you can lift it. This is what this is saying. They're compatible, these two pseudo representations. You can lift the individual traces and determinants to the T function and the D function. Somebody should have complained here. The T. You can lift the individual traces to a 1T function and lift the individual determinants of these two pseudo representations to 1D function. Suppose you can do this, they're compatible, these two pseudo representations, at least on a dense set. Then there's a genuine pseudo representation. Not genuine, but a pseudo representation. We're patching pi on the intersection such that, well, the trace of pi of A intersection B is T mod A intersection B, and the determinant of pi of A intersection B is equal to D mod A intersection B. Okay, so you can somehow glue them together. If they already agree on, if they individually come from some D, then you can actually find something which takes values in I mod A intersection B. And the point of this is that A intersection B is smaller, so you've come a little bit closer to constructing a pseudo representation into I. So just from the T and D functions, which are I valued, you've come a little bit closer to constructing a pseudo representation, not just T and D functions, but the pseudo representation is a little bit closer to being I valued. As you intersect more and more of these ideals, this will get smaller and smaller, and you'll get approach I. Okay, and so what's the proof of this? Well, we note the following exact sequence. This lemma is something that once I write it down, you can actually prove it as a homework problem. But let me do the proof. It's more or less obvious what you have to do once one writes the statement of the lemma down. So this map is just A bar, B bar goes to A minus B bar. And this map is A goes to A bar, A bar. Diagonal map, and then this is the difference map. So clearly, if you take the composition, you get 0. And the kernel of this is that, etc., etc. Exact sequence. Okay, so how do we define pi? Well, we'll define pi to be, let me not write A intersection B each time, but let me just call it pi. To B, we take pi of A, direct sum pi of B. Okay, so a priori now this is not good because this is actually taking values. This is not good because we wanted to take values in I of A intersection B, right? Well, what do we notice? This is going to be pi intersection A, pi A intersection B eventually, but let's notice for now that the trace of pi, which is the trace of pi of A plus the trace of pi of B. Well, what is this? It's basically T and T, right? By these conditions up here, T and T. And what happens to this thing, this ordered pair, when you push it over here? Well, T minus T goes to 0. Right? At least if you're on this dense set on sigma. Dense set of Galois elements. Okay, but I'm claiming that in fact forces the trace of pi to be identically 0. So you can think about that for a second.
So is it a two tuple or is it a plus this trace?
It's it's a tuple. Yeah, maybe a tuple. Yeah, you're right. Sometimes in the sum I'm thinking of as an internal direct sum and sometimes as an external direct sum. But anyway,
Thanks.
So yeah, so I was saying that this function goes to 0 because on a dense set anyway it goes to 0, and 0 is a closed point in the topological ring. So by continuity it'll go to the closure on the whole thing. Trace is continuous. It's a sum of continuous functions. Trace is continuous, so it'll still be 0 on the whole thing. So what is this saying? It's saying that the trace of this, let's keep this as a parenthesis for now. Huh? The pi is just this abstract thing, but it's eventually going to be what I want to be pi intersection A. So trace goes to 0. So therefore, trace of pi takes values in I of A intersection B, right? Because it went to 0 under this map, so it's in the kernel of this map, so it's in the image of this map, and we can think of. So we just shown that trace of pi takes values in A intersection B, okay? Is everyone okay so far? Right? So I didn't do anything so serious. I just checked that some abstract pseudo representation. By the way, this is actually a pseudo representation. Sum of pseudo representations is a pseudo representation. That one has to check. Sorry, my daughter is calling every few seconds. Let me just. Okay, the joys of teaching on a weekend. All right, so trace of pi takes values in I modulo A intersection B. I know it's my children calling when they call 5 times until I don't pick up the phone, they'll keep calling. All right, so we have something in here, but now I'm going to use a little trick. It turns out that the A and D functions can actually be recovered from the trace functions. Notice I didn't say anything about determinant here, huh? Because everything is, I don't need the determinant. The A function, if you just think about it for a second, is the sum for any pseudo representation. The A function is the trace function precomposed with complex conjugate, the C, this is the C of an entry. So by this I mean it's A of sigma is trace of sigma plus trace of C sigma divided by 2. It might be sigma C, but I hope it's C sigma. I've got the composition order. This is what I mean by that anyway. And D is equal to trace minus trace of composed with C over 2. Since I have a slight doubt here, let me just check my original notes. I'm writing things just with shorthand. Yeah, so by this I mean that the A of sigma is trace of sigma, trace of C sigma divided by 2. And this is trace D of sigma equal to trace of sigma times trace of C sigma. You multiply by C in the front. That's what I was so unclear by. So it turns out that these two formulas are true just by looking at, right? These are obvious more or less. Okay, so once you know that the trace takes values in I intersection B, from this to computations, we see that, I'll keep it here for a second. So A of pi and D of pi also take values in I mod A intersection B, right? Because the trace, we showed the trace takes values in I mod A intersection B. We made the ring a bit smaller. And because of these formulas here, A can be completely determined by the trace functions. We see that A and D can also take values in I mod A intersection B. Okay, very good. Well, I'm finally claiming that X of pi also takes values. Therefore, X pi also takes values in this. And why is that? Well, for that we go back to one of our axioms of pseudo representation, and I think it's just the first one, for instance. If you look at the first axiom for pseudo representation here, right? If A takes values in some ring, then X clearly takes values also in that ring. In fact, I should have made the remark that when you define a pseudo representation, you don't even have to include X in the definition, because X is completely determined by A. Okay, X sigma tau is given by this formula, A sigma tau minus A sigma A tau. So X is completely determined by A, or by this, by D, whatever you want to say. So you don't really have to include X in the notation, but I did just to make it a bit more balanced in terms of the notation. In any case, once you know that A and D are I mod A intersection B valued, then X is also I mod A intersection B valued. Okay, and then we set pi of A intersection B, because everything now is in the right ring to be pi. So I should have put this notation maybe at the end, but there's motivation to say that that will be the representation. So we have constructed a representation, pi of A intersection B, and it is easy to check that it has the properties that I just stated here.
Sir, I have just one confusion.
Sorry?
Yeah, just one confusion I have.
Yes, yes.
Yeah, so we had this pair T and D.
Yeah.
In the statement and in the proof, just we said but A sigma is equal to this. So
yes.
And D is equal to D of sigma is equal to this. So
yes, yes.
this A is what?
These are general formulas for pseudo representations in terms of the trace function of a pseudo representation.
Yeah,
so general facts. So if you look at my old Guwahati notes, these were coming from some formulas I proved in properties of pseudo representations.
Okay, so these.
I'm saying that these are just formulas which say that whenever you have a abstract pseudo representation, not in the setting of this patching lemma, whenever you have a pseudo representation ADX with trace A plus D, then you can recover the A and D functions from the trace function.
Okay.
Because this is like A plus D and this is like A minus D, so the D's cancel and divide by 2. So you can recover A from the trace, and similarly you can recover D from the trace. So that's all I'm saying. So as soon as you know that the trace is taking values in some ring, then immediately the A and D functions also take values in that ring.
So these follow from your 7 axioms or?
No, this is just a definition. This is this is just a very simple computation. Yeah, maybe. Yeah. the trace of sigma is A of sigma plus D of sigma, and the trace of C sigma is the A of C sigma plus D of C sigma, and then you have to look at what A of C sigma and D of sigma. It's a small check, right? Things will cancel.
Yeah. Okay.
Yeah. The A of C sigma is probably just A of sigma by one of the axioms, and the D of C sigma is probably minus D of sigma. So the D's will cancel, and you'll get 2A, and then right.
Okay. Okay.
Some computation like that. Yeah. Okay. Good question. There was something to be said there. A little computation to be done. So these formulas were just some black boxes, but they're easy checks. I thought you were going to ask another question, whether the final pi that I wrote really had this final property that the trace of the patched pseudo representation was coming from this function T and D in the trace and determinant of it. But that's almost by definition of the construction of it, because we had chosen it so that it was in the diagonal elements here, right? So therefore, the values on some things are going to be diagonal things. So you'll get TT and DD and things like that. Okay, so there's something to be checked here also, that the trace of pi intersection AB is T mod A intersection B. Right, because it was TT here, and the way it's TT here is only one way. If it's T here, the trace. So that's why it's T. Okay, so these properties are obvious if you think about them, but I'm not writing the proofs down. All right, so 28, 29, very good. So can I finish in 7 minutes? I hope I can. I'm going a bit slow. All right, so very good. Fortunately, my last page is just definitions. So now, with all this stuff, we can finally give a proof of theorem, the construction of the Galois representation, the Lambda-adic Galois representation. Proof of theorem, lambda 1. Okay, so let sigma be the Frobenius elements. This is our dense set in which we're going to apply the patching lemma. I'll go a little fast now. It's a dense set. And then let T be the, let's apply the patching lemma to these functions. The ALF function, and D, the determinant function, which we already have seen now. Okay, so remember this is I-valued, so that's why. So let's look at these special functions, T and D. These are our big global functions which will patch things together, T and D. And they're coming really from the Galois representation secretly, huh? That's good. But for now, they're just some abstract functions. Okay, and finally, let us write all the kernels of all the news, the arithmetic specializations. Let us write these kernels of these homomorphisms. They're height 1 primes. Okay, so they're not minimal primes, and they're not also, they're not 0. Minimal primes are 0, and they're not also maximal ideals, which are height 2 primes. They're in between. So these are height 1 primes. They're prime ideals, but it's a kernel of a map, taking values in a domain. So I'm on the kernel is a domain. But so let us, there are many k's, k greater than or equal to 2, and zeta in mu p r minus 1, r greater than 1. I said I would go fast, but I'm going slow again, recalling on the notation, right? And then there are finitely many extensions for these countable sets. So still, this is a countable set of height 1 primes. So let me number them and call them Pn for n equals 1 to infinity for simplicity. Okay, countable set of height 1 primes. But this an infinite set is all we really need of I. Okay, and then let us write pi of pi for the pseudo representation attached to rho pi. This rho pi is really the, it's Do you know what I'm talking about here? Each pi corresponds, each of the height 1 primes is really a specialization map. So you really have a genuine modular form. And once you have a genuine modular form, you have a genuine Galois representation. So that's what this notation is. So this is a genuine Galois representation attached to this height 1 prime, and then you take the pseudo representation attached to that. Right? That's what we want to do. We have the genuine, that's that square that I wrote at the, halfway through the lecture. We have the pseudo representations attached to the genuine Galois representations, and now we want to patch all these together. Okay, so the remark is then the pi pi are compatible in the sense of the lemma. Right? And this is now, I won't write a proof of this, but this is obvious because we just checked that the individual traces and determinants of the classical representations are coming from a lambda-adic trace and determinant, these T and D functions. We did that computation at the beginning of the lecture. So there are these T and D functions which interpolate at least the trace and determinants, right? So they're compatible as in the hypothesis of the lemma. So by the lemma, and the lemma is only for two things, and induction, where you have to do this again and again, which I'll skip. You first patch P1 and P2, then P1 intersection P2 with P3, and so on and so forth. You get a pseudo representation phi of A intersection B, but I'm taking many, many primes now. So I equals 1 to J, let's say, Pi from the Galois group of Q bar over Q to I of the intersection, I equals 1 to J. Right? With some property, which was the conclusion of the lemma. But at least you can glue these finitely many pseudo representations together to get one on I mod the intersection. Okay, so as I said, I'll go a bit fast now since I'm running out of time. You let J go to infinity, and note that the intersection of countably many height 1 primes is 0. And note intersection I equals 1 to infinity of Pi equals 0. And get a pi from the Galois group of Q bar over Q to I, which whose trace is T and whose determinant is D, these particular T and D, which are up here, T and D, which are up here on at least on a dense set of primes, and actually on all of G. So now we've got a pseudo representation with values in I. Are there any questions about this step? It is, I hope at least conceptually clear, even though I didn't do the inductive step. Any questions on this? So each of the pi pi's was a pseudo representation, and I glue together pi p1 and pi p2 by the lemma. And then I get something on I modulo the intersection P1 intersection P2. Then I take my pi P3 and do that in furthermore using the lemma, so on and so forth. And then there's something one has to check about J tending to infinity, but it's very believable you can do that. And these things get smaller and smaller. They go up to 0, the intersection. So you actually get values in I modulo 0. Okay, so there are some minor checks there, and you can look at the notes from many years ago, or Hida's book, the blue book, where a lot of this argument is taken from. I think we gave much more details than Hida's book, but in any case. Okay, so I'm almost done. But now we have a pseudo representation which is I valued with good trace and determinant, right? Because T and D were like good for us. But unfortunately, this is not a Galois representation. But now by the corollary, there's only one corollary in all the lectures I've given in the last 7 hours, and if you include the discussion section. And that was, it's uniquely determined, the corollary, but let me flash it in front of you if I can find it. Yeah, It's at the bottom of page 27. If B is a topological field, then pi always comes from some row, that corollary. Well, here we don't have a field, but I is sitting in a field. It's sitting in K or K sub F, because everything depends on the lambda-adic form. The trace and determinant functions depend on the data attached to the lambda-adic form. So by the corollary, we now get pi comes from some row from the Galois group of Q bar over Q to GL2 KF. And let me just squeeze this in here. Note, there should be another page for this, that the trace of rho, this is the classical trace, so I write the small trace here. The trace of rho is, since it comes from pi, it's the trace of the pseudo representation, which is the Lth Fourier coefficient, at least on the Frobenius L elements, Frobenius L. And similarly, the determinant, I'm running out of space, but exactly the same thing, the determinant of rho, since it comes from pi, it's the determinant of the pseudo representation, which by definition at the top of the page was psi kappa nu inverse. Psi kappa nu inverse. Okay. So because of those two things, and then I'll just write the last line. Can you see? We set rho F to be rho and obtain theorem lambda 1. Okay, so this is how the Galois representation is constructed. You patch together the individual pseudo representations to come up with pi, and then you just artificially think of pi as taking values in this field, and therefore pi comes from some row. And if you try and compute the trace and determinant of this row, well, they're good. They're good things. They're exactly the trace and determinant of the theorem of the Galois representation in Hida-Weil's theorem. And therefore, by two functions have the same trace, if two Galois representations have the same traces and determinants, they have to be isomorphic. Okay, so this is the representation in theorem lambda 1. Remark, theorem lambda 2 is proved similarly. Similarly, gluing together the information provided by theorem 2 for all arithmetic primes. Very similar argument, okay? Which I was not planning to do in this course, but I already sketched theorem 1 and it's very similar. If all the specializations are upper triangular, then the lambda-adic representation locally will also be upper triangular. Okay. I'll stop here, but I will flash some references after you're done asking your questions.
So I have a question, like for primes other than P, like dividing the level, does one have some reducibility or anything, or that is not there?
So, sorry, for primes dividing the level?
Yeah, I mean other primes, because now this theorem is about primes.
You can ask, that's a good question. You can ask that question, you can ask that question even classically. So if you take a classical p-adic Galois representation and take a prime L, which has nothing to do with the level or P, or maybe even divides the level, you can ask what the Galois representation looks like at primes L. That's completely understood. There's no mystery there.
I see.
So for example, yeah. So for example, at a prime L, which is of Steinberg type, where L exactly divides the level N, then the image of inertia is already infinite. There'll be some unipotent elements like 1101 in the image of the Galois representation, which you can never kill. And so the image will be infinite and things like that. Yeah, those things have been understood. Those things are completely understood. There's no mystery there at all. So the LP Galois representation is very well understood. In the domain you have an L, and in the range you have a P. Depends on whether your local factor of automorphy of the corresponding automorphic representation is principal series or Steinberg or supercuspal, etc. And depending on those cases, one can write down the shape of the Galois representation immediately. For example, in the supercuspal case, it's an induced representation from a quadratic extension, etc.
Okay, I have another question.
Yes.
Since you said there are only finitely many primitive lambda-adic forms,
Yes.
does it somehow limit the dimension of the ordinary space of, classical modular forms? Is it like?
No, it only controls the slope zero space. The slope is the p-adic valuation of, p-adic valuation of the p-th Fourier coefficient.
Yeah.
And p-adic valuation of the p-th Fourier coefficient is when it's zero. The p-adic valuation so the slope, when the slope is zero, you get information about those eigenforms. So the number of what Hida has proved is that the number of slope zero eigenforms, as you vary the weight and you rotate the Navier-Typus in the right way, the number of slope zero eigenforms is a constant, and they all glue together. It's like I'd like to draw this picture of a ladder. So this is like weight 2, this is weight 3, this is weight 4. So there's this dimension of the space of modular forms, which is becoming larger and larger in every weight, right?
Yeah.
But the number of zeros that you get for the slopes, suppose there are 5 of them, those remain constant. Right?
Nice.
Some 1s, some 2s, some 3s, I don't know, maybe some 1.5s, 3, 4, 5, 5, 5, 6, right? Some different slopes. But the number of zeros that you get will be more or less constant. And these things form a ladder. So this is in some space where the Navier-Typus is rotating, by the way. So some people don't like that. They don't like Navier-Typus. They want to work with gamma naught n and not gamma 1n. But then you can also do that by saying that the two weights, if they're congruent modulo p minus 1, then the Navier-Typus character is fixed because the power of omega is the same. And in that case, you can then just skip every p minus first row and make the same statement. But I want to emphasize it's really for every weight. People often ask this to me, whether it's for every weight or the weights are congruent modulo p minus 1, because in the old days, people used to work with gamma naught n.
Okay, thank you.
Sir, I have just few queries. So
Yes,
this Galois representation attached to lambda-adic forms, this so it interpolates with the modular form Galois representations.
yes.
But when we have modular form Galois representation, we go from Galois q bar over q to GL to KFP.
Yes.
So completion of that.
Correct.
On the other hand, in this Galois representation attached to lambda-adic form, it is just F. So this special P with the modular form Galois representation, it has something to do with P ordinary. What we define?
Yeah. So that's a very good question. So KF, K little f completed at strict P.
Yeah.
You think of that as embedded in QP bar.
Okay.
So I could have, and I probably should do that the next time I give this course, instead of writing the field in which the classical Galois representation takes values as GL2 KF completed at Weierstrass P, just write it as GL2 of QP bar. Then it becomes much more clear, I think, that the lambda-adic Galois representation, because the specialization map is under I goes to QP bar. So you can see that the lambda-adic Galois representation, when you specialize the field, it will go to QP bar. I think that's your question, but yeah, I'm explicitly fixing embeddings of number field completed at Weierstrass P and QP bar.
And that P, this P ordinary for which we define.
Yeah, once you fix once you fix the embedding of Q bar into QP bar, that fixes all your Weierstrass P's for all of the finite extensions, and that also fixes the P ordinary condition. It's ordinary with respect to that Gothic P. You're right.
Okay.
Yeah,
okay.
Yeah.
And just another thing is this capital N, this tame label, if I take tame label 1, whether
Yes.
theory gets somewhere simplified and
Sorry,
I can,
if the T level is 1,
then some simplification will happen or some special thing will happen where easy to understand. Since in modular form, that's what happens.
Yes. The thing is that lambda-adic forms always have a p in the level anyway, so you can never really have anything of genuine level 1. The level is really n equals 1, but there's an np because all the modular forms are of level p anyway. So you don't see anything purely for SL2Z. But for example, you can ask, what is I? Maybe let me just ask this question since we're at the end of the course. Like the rings I, like, I said Q root 144169 you get in the tutorial. You get that for the modular form of weight 24 and level 1. So there's some explicit number fields that show up as the field of Fourier coefficients of classical cusp forms. What about for lambda-adic forms? What are the fields of Fourier coefficients of these lambda-adic forms? Maybe for level 1, one can try and write them down and they're a bit simpler. So for example, is I always of the form a finite extension of ZP power series X? Those are very special kinds of extensions of ZP power series X. Because I just extended the coefficients, I didn't extend. But one knows for sure that that's false in general. And there's some very interesting lambda-adic rings that come up. And some of them are in my papers, you can try and look. But I think it's an open question to classify what kinds of rings show up as the rings of Fourier coefficients of lambda-adic forms. And maybe in level 1, since you're asking about level 1, that question is a bit easier to answer. I vaguely remember some work of Hida or maybe Greenberg, Stevens, or Fishman, where they say that in level 1, and maybe there's some other conditions, that these rings I are simpler. They're just the rings that I just described.
After combining coefficients.
After?
So just after this coefficient, after combining coefficients to I.
Yes. Yeah, the coefficients I become a bit simpler in level 1. But this is a new subject, and there's many things to be done here. So it's and this problem is anyway open for classical modular forms, which are at least 100 years old, maybe more, a few hundred years. So yeah, there are many interesting elementary questions to be asked.
Okay, sir. Thanks, sir.
Maybe let me, since it's being recorded, let me flash this one slide with the references. To page 31, I just changed the page number because I took it from my old notes. And I'm not going to write the whole thing, I'll just flash it. So there's a remark here, maybe I'll read that. As I was saying that the lambda-adic Galois representation is upper triangular. And you may ask about this star, whether the star is 0. And I said I wouldn't talk about my research, but I noticed some people have. So here is a theorem which says that star is 0 if and only if M is a CM family. And we talked about this a bit in the discussion section outside the course. This is under some mild conditions, the theorem from 2004 with Bansal. So there's some very nice information about that star, and it's an open problem to check what this star is for classical forms. Okay, so that is one thing we talked about in the discussion, how this lambda-adic information gives you classical information. That's one remark, and then I will now flash the references, which I hope are fitting on the page. Are they fitting, all the references?
Yeah.
Okay, so as I said, these are the Guwahati lecture notes from, not 12 years ago, 10 years ago, because I think it took 2 years for it to publish. The conference was in 2008. But by the time these lecture notes came out, it was 2010. And then there's the pink book of Shimura, the blue book of Hida, and the yellow book of Washington. Right, so these are the sort of main references. Maybe Hida's book is more important for this course because chapter 7 contains the information about the lambda-adic forms. And I use some classical facts about elliptic curves and modular forms from Shimura's book, and Heck operators and things. And I use some facts about p-adic functions, Kubota-Leopold p-adic function, Sawa theory from Washington's book. And let me finally mention 2 papers. So there's some papers with Vatsal. Just quote one of them here. So that's the paper I mentioned just now, a few seconds ago, 2004, analysis to Fourier. And if you're ever interested in what happens at the prime 2, well, Narasimha Kumar and I spent a lot of time when he was a student at TIFR trying to work out some details about that. And it's notationally quite heavy, but one can say some new things and prove analogs of the main theorems of Hita theory. So that is described in this long paper with Narasimha Kumar. It appeared in a TIFR conference proceedings in 2013, one of the IC colloquia proceedings, international colloquia at TIFR. We have those, one of those proceedings. Okay, so I will end with that, but the main 2 references maybe are these 2, the 0th one and the second one. Okay, all right, so thank you.